So we're into a chapter called Thermodynamics, and I like to break it up into a couple of different sections. And in the first part, I like to give an overview of what thermodynamics can and can't do. And I also like to review thermochemistry. Thermochemistry is the first portion of thermodynamics, and you learned that when you took the first semester of general chemistry. So let's sort of talk about what thermochemistry is, right? Thermochemistry is where we discuss the first law of thermodynamics. First law of thermodynamics, simply put, is the conservation of energy. And so in chemistry, we usually break energy down into a couple of different kinds of energies. We talk about heat energy and we talk about work energy. And heat energy is essentially the transfer of heat energy is sort of like driven by temperature differences. And then there's work energy as well. It's like what kind of work does the chemical reaction do? Now, work energy, we'll talk about this more later, is related to what's called pressure volume work. Because that's the way, as chemists, we sort of think of how a chemical reaction could produce work. For example, by creating pressure and a change in volume as you drive a piston in a car engine, things like that. Heat energy we usually think of as transfer of chemical energy, but normally when we start our discussion of thermochemistry, we start with a cup of water and a piece of metal in something called calorimetry. Nice. It's erasing as I write. Let's try it again. There we go. And calorimetry is really the measurement of calories, and calories is the older unit for energy. Typically, we do everything in the units of joules now. But calorimetry, the name stuck first. So it's not called joulerimetry or whatever you want to call it. I mean, that would be a weird name for that. So we do calorimetry. So let me explain to you how we use conservation of energy with calorimetry to figure out how much heat energy is transferred. So the sort of standard experiment that we start with is a coffee cup. Or the coffee cup is supposed to represent a calorimeter, but it turns out an insulated cup, like a styrofoam cup, is a pretty good calorimeter. It basically prevents the loss of heat from the sides. And so it's basically just an insulated cup, okay? And then we put water in it, and the water has a temperature associated with it. We'll call it TW. And then we put a piece of metal in there that's at a higher temperature usually. So we usually heat that metal up for a good period of time. We stick it in the water. Let's say the water starts out at 25 degrees Celsius, which is sort of the standard room temperature. And let's say the metal in these experiments is typically around 100 degrees Celsius, because the way we heat it to 100 is we just put it in boiling water, and then we wipe the excess water off, and then we throw it into the cup. Okay, so assuming the cup is a perfect insulator, right? And what does that mean, right? There's no energy lost through the walls of the cup or from the top of the cup. And that's kind of a make-believe thing, but in the time frame these experiments are usually done, it's a pretty good approximation. When you hold the styrofoam cup in your hand and you pour hot water into it, it doesn't get hot right away, and that's about the time frame it takes for these experiments. So if the cup got hot right away, then you would know that lots of heat was being lost by the calorimeter, right? So a styrofoam coffee cup, sometimes we double them up and it improves their performance and all that kind of stuff. Okay, so what happens to the temperature, right, of the mixture of the metal in the water over time, right? There's going to be a T final. And T final represents what we call thermal equilibrium. Now, the heat energy, the transfer of heat energy is driven by temperature. So when you have a temperature difference, the energy, which is really like kinetic energy of the molecules inside the object vibrating, that energy transfers from one object to another. as long as something's hotter than something else, that energy will transfer. So the metal will be transferring energy into the water. Eventually, the temperatures will be the same, right? And when the temperatures are the same, the heat energy can't transfer. Okay, so energy is something like an object can possess energy, but heat is actually the transfer of the energy. Okay, so let's say we wanted to figure out how much energy was transferred from the metal, right, to the water. And let's say we didn't know anything about the metal other than its mass or its initial temperature. Okay. Well, the way we would figure it out is we would first of all think about this problem as there's heat energy, and let me use a different color so it sticks out. Oh, sorry. Loud noise. I'll use green. Heat energy is transferring to the metal to the water is warming up, the metal's cooling down, right? Well, what we would say is that the heat of the water plus the heat of the metal is equal to 0. Now, conservation of energy, this is a conservation of energy statement. Conservation of energy would tell us that if we wanted to know the heat that was lost by the metal, all we need to do is figure out the heat that was gained by the water. And that would be, right, the heat of the metal would be the opposite of the heat of the water using the first law of thermodynamics or conservation of energy. Turns out oftentimes it's easy to measure this because we have an equation it's often called MCAT equation. It's Q is equal to mc delta T. And we can use the mass of the water, the specific heat of water, C for water. Oh, that's a horrible color there, sorry. C for water is equal to 4.18. 4 often is given another decimal, joules per gram degree Celsius. So you could have the specific heat of the metal, you could have the mass of the water, and you can actually just measure what temperature the water started at, and then you measure the final temperature of the mixture, and that would give you T final. And by the way, T final, right, delta T, is always T final minus T initial. So in this way, we could take a metal, right, throw it into water, and figure out how much heat energy is lost by it. Now, that's really kind of like a physics kind of thing, right? It's a measurement of heat capacities, measurement of heat transfer for something like a metal object. That's something that's often done like in physics. Now, on the other hand, we do it in chemistry a lot too, but here's what we're actually doing, okay? You often have a Q for a reaction. So let's say we reset this experiment. I'll do a small scale version of it here. And for aqueous reactions, we can run them in this calorimeter cup. So you have H2O in here, plus a chemical reaction. And what we can say is that the Q for the water plus the Q for the reaction, that equals 0. In other words, if we wanted to know how much energy was either released or absorbed by the reaction, right? All we need to do is measure to see what happens to the water, provided that we have a decent calorimeter, right? And a coffee cup turns out to give you, like, usually answers for quick reactions, usually gives you answers within 5% on a good day, right? On a bad day, it might be more like 20%. But on a good day, you can get 5% accuracy just out of a coffee cup as long as the reactions happen fairly quickly. And there's a couple other factors, but basically that's the idea. So this is what thermochemistry attempts to do, is to measure energies of reactions by using the first law of thermodynamics, and then we use those energies in a lot of different ways. Okay, so let me talk a little bit more about how we're studying what we're studying. So what we're always doing in thermochemistry and thermodynamics is we're talking about the system and the surrounding. And it's pretty simple to sort of define the two. The system is what we're studying. So for chemists, that's usually a chemical reaction. And then for the surrounding, that's just everything around the chemical reaction. So in the example that I just gave, the system would have been the chemical reaction. The surrounding would have been the water, And it could have been the cup and other things, assuming the cup didn't insulate well. But if the cup's a really good insulator, the system is the reaction and the surroundings is the water. So when we think about energy transfer, remember when we're doing conservation of energy, we're saying things like Q of the system is equal to negative Q of the surroundings. And to get this thing to be this kind of work to be accurate, we really have to define what it means when the system absorbs heat energy or gives off heat energy, okay? And we also have to define what it means when a system does work or work is done on the system. Because this will have a difference. You can sort of basically understand that if you're doing work, you lose energy. If someone's doing work on you, like giving you a massage or whatever, you're gaining energy, right? So that's one of the things we have to straighten out. So we often visualize it with a piston. And the reason we're doing pistons is because in chemistry we think of work as being related to pressure times a change in volume. So why, right? Well, one of the ways we use chemical reactions to do work, because it's hard like to think about like how do you get a precipitation reaction to do work, or how do you get a combustion reaction to do work. The way we get it to do work is we allow there to be a volume change at a pressure. And so when a reaction, for example a combustion reaction like in an internal combustion engine, produces its products, what it's producing is gas, which then expands, and that expansion does the work. So a simple equation for that is work is equal to minus P delta V. And then pressure can be in atmospheres and volumes can be in liters. And it turns out 1 liter times 1 atmosphere, so 1 liter atmosphere, is 101.3 joules. And this is a pretty handy conversion that we use for determining like how much work a gas does when it's produced by a chemical reaction. Okay, so here's our piston. And if heat energy is going in, right, we have to define the system and the surrounding. So the system is the piston, and then everything around it is the surrounding. So if the heat energy is going into the piston, then what we say is Q is positive. This would be analogous to an endothermic reaction. Q cis has a positive value. It's endothermic. Now, how do you know when you have an endothermic reaction? Because it feels cold when you touch it because it's absorbing the energy, or it feels cold, right? That's the idea. Now, if heat was coming out of the piston, right? Imagine it doesn't move. So basically you're heating it here, right? And then you're letting it cool here. And when you're doing that, heat is leaving, then Q will have a negative value. So in other words, the system is losing energy to the surroundings. Now remember, the surroundings is always the opposite. So if the piston's losing energy, the surroundings gaining energy. Conservation and energy statement would say those two added together are conserved, so it equals 0. Now, if you're doing work, so here's the piston, right? And you're doing work on the surroundings. Notice that the volume is going up. Delta V is positive. But by pushing up, like imagine you're a little guy in here, right? And I don't know why you would be in here. And your weird long monkey arms. And you're trying to push that piston up, right? You're losing energy by doing work on the surroundings. So that's why W is negative here, right, as the piston expands outward. You can think about a chemical reaction that's producing a gas, for example, like in a car, right? Like I was talking about a piston in a car. That some of that energy from that reaction is being used to drive that piston. On the other hand, when the piston is pushed downward, right, then the work energy of the piston goes up. Again, you know, that would be, I guess the analogy would be a massage or something. But you know that this is the case if you've ever pumped a bicycle tire. If you push the bicycle tire handle down, you're basically putting work energy in to a piston. And if you let go of it too fast, what happens is the handles will shoot back up to release that energy. And so then it's doing work on the surroundings when it's going upwards, and when it's going downward, it's absorbing energy. So W is positive in those instances. So real quickly, how do people measure reaction energies? And I've already talked about it a little bit back here when I talked about the coffee cup calorimeter, right? There's other ways that it gets done, and another one is to use something called a bomb calorimeter. Calculations are essentially the same. So in a bomb calorimeter, it's basically a well-sealed environment, okay? And then what we have inside here is a small metal box. It's called bomb calorimetry, where we have our chemical reaction that takes place. And then usually like a combustion reaction, let's say. So we put oxygen in there. It's usually pressurized, and then you get a product out of it, which is usually CO2 and water in these reactions. Especially if you run with an excess of oxygen gas. Right, and these are often in the gas phase because they come out of the reaction. And then this can be a solid, liquid, or a gas, really. It could be any of those things. And then from that, we can measure the heat energy. So we basically ignite this stuff in the bomb, and then it releases energy like this. Now, this is slightly different than the coffee cup calorimeter, but it's a completely valid way of measuring the energy of a reaction. And this is usually how they measure, for example, the energy, the calories contained inside of food, right? The difference, though, in bomb calorimetry versus the coffee cup calorimeter is that this is done at a constant volume, whereas a coffee cup calorimeter is done at a constant pressure. Now, when we're doing reactions that occur at constant pressure, what we call that quantity is actually the enthalpy. So here's an example of a thermochemical equation, and this is the reaction enthalpy, delta H, of reaction down here. Get rid of that. Delta H is the enthalpy of a reaction which takes place under conditions of constant pressure, basically, instead of constant volume. And so this is the heat energy that's released by this particular reaction. So how would we use this information? Well, we can use the information, for example, by doing calculations for the heat energy that might be released by a reaction. So we have 2.89 grams of ethane gas. So this is 2.89 grams. And we want to calculate the energy released. So we treat this quantity just like we do stoichiometric coefficients. So if we had 2.89 grams of C2H6, the molar mass for ethane is around 30.047 grams for every 1 mole. And then when we want to calculate the energy, we use the negative, right, 3,119.44. as sort of like the stoichiometric coefficient for kilojoules, and then we divide by 2 moles of C2H6, like that. So when we do that calculation anyways, then we'll end up with the energy that's released for 2.89 grams, and that comes out to be 150 kilojoules. 1.50 times 10 to the 2. Yeah. Okay, so that's how we would do that. And then we can also get the enthalpy of the reaction different ways other than a calorimeter. And a standard way to do it is to use the standard heats of formation that are found in the back of your textbook. Okay, so what we're going to do is I'll show you how to find the standard enthalpies of formation in Appendix 2, and then we'll go ahead and calculate this reaction enthalpy. So we'll go to the back of the textbook into the appendix. Let's see here. Oh my, there it is. And you'll notice that I'll go back to the beginning of this appendix so you can see the top of the page. Again, this is Appendix 2. It's in the reference material section in the Canvas page. So you'll notice, for example, there's like aluminum here and aluminum gas and aluminum 3+ ion aqueous. There's a bunch of different states. Again, some things will be in 2 states, some things will have 3 states of it. So you'll notice that the standard enthalpy of formation for aluminum is 0, but aluminum gas is 330.0 kilojoules per mole, right? So let's talk about what that actually means. So if I have aluminum as a solid and I write this reaction, okay, and I ask you how much energy would that take, and you would look at that and look at me and go like, well, 0, right? And hopefully that's what you come up with, because it is 0. Basically, this reaction says, how do you make aluminum solid from aluminum solid? That's going to basically take 0 energy. So this is 0.00 kilojoules per mole, or kilojoules for the reaction as written. Now, let's say you looked at the reaction of aluminum solid to aluminum gas. This turns out to be what takes 330 kilojoules. Aluminum solid is known as the reference form. And every element has a reference form. And normally it's what you would expect it to be from the periodic table. So for example, oxygen that's here, you expect that one to be 0 because oxygen O2, right, is one of the diatomic gases, and that's the way we most commonly find it in our atmosphere, for example. But it's one of the more stable forms of oxygen. Aluminum is, as a pure element, found as aluminum metal, although not rarely, because it's actually pretty reactive. And bromine, Br2, is a liquid, and so when you go to the back of the appendix, right, Appendix 2, and you look at for bromine, go to the next page, of course. Br2 liquid, that's the reference form for bromine. So basically it's saying, well, if I want to make bromine liquid from bromine liquid, it'll take 0 kilojoules per mole. On the other hand, if I want to make Br2 gas, it's going to be endothermic, absorb energy, and require 30.9 kilojoules per mole. So we have reference forms for every element. Now, if something is like CH4, gas, right? The way that that is formed is from carbon as a solid, which is graphite. That's the reference form. There's several pure forms of carbon that you find in nature, diamonds being one of them, right? And hydrogen gas. And that would be the reference equation for methane. And then again, we call both of these 0 on a relative scale, so we can get the energy for this. So if you go back and you look up the values from the back of your book, you'll find listings like these. And so like for methane, it's minus 74.6. Oxygen would be 0, right? CO2, right, there's a couple of choices, but this is CO2 gas, so it would be minus 393.5. And then we would have to go look up water in the gas phase. And the thing that's a little weird about these tables, but you get used to it after a while, it's either going to be listed under oxygen or it's going to be listed under hydrogen. And after a while, you'll figure out hydrogen's not usually where things are listed unless it's like hydrogen. And then everything else to be listed by the second element for compounds of hydrogen. But carbon dioxide, right, you're going to look at based on carbon. And you would find, for example, these two listed together. Because they'd both be under carbon. And carbon has a huge section, so I just sort of pulled these ones out so you could see where they're at. Now, actually on the next slide, I already have the values, so what we're going to do is we're going to go ahead and calculate the delta H of the reaction. And the way we're going to do that is we're going to take, well, there we go. Delta H of reaction is going to be products, delta H of the products, minus delta H of the reactants. But remember, these are all given in units of kilojoules per mole. And so if you have 2 moles in the reaction at any point, here included, well, it doesn't matter because it's 0, you have to multiply this value by 2 to calculate the energy of the reaction, because it is per mole of this substance. So then what we would write is delta H of the reaction is equal to, and then I'm going to write this out like this, it's 2 times negative 241.8, and I'm going to leave the units off, but it's 2 times the kilojoules per mole, so 2 moles times that would just leave me with kilojoules. So I'm going to write the kilojoules at the very end, otherwise we often run out of space for this, plus 1 times CO2, so that would be minus 393.5, and this is for the CO2, this is for the so this is for the H2O, and this is for the CO2, and so this makes up all of our reactants, and then we're going to subtract from it, and then it's often helpful to write a giant parenthesis there, minus 1 times 76.4. And then I'm going to leave the oxygen out because it's 0, and I just have to do that calculation. So where people usually struggle with this is actually in this part of the calculation, because you have negatives of negatives. So basically I just tell people add all these things up that are inside the brackets, add everything up inside the brackets over here, and then do the subtraction. It's a little easier to keep track of the signs. We'll go ahead and we'll pull up a calculator here. So we're going to go, it's on top of the, oh, that did not help. Get it out of the way. There we go. So I'm going to do 2 times and then 241.8 change sign plus, I'll not do the 1 times, but 393.5 change sign. That comes out to this negative 877.1. Oh, I forgot my kilojoules, right? So that'll be kilojoules for that. Minus, and then it's going to be minus a 76.4. So minus a minus 76.4 kilojoules. So we'll go over to here, and if you want, you can just add, right? Same thing, but I'm going to go ahead and say minus, and then 76.4 change sign, and I get 800.7. So if you were to write this out as a thermochemical equation, then this would be delta H is equal to minus 800.7 kilojoules up here. Okay, so that's how we get those numbers, products minus reactants, and they're found all in the appendix in the back of your book. And one of the reasons I'm showing you this is because you're going to have to do it with something called free energy and also with entropy, and the calculations are done the exact same way. Products minus reactants taking into account the stoichiometric coefficients. So what we're going to do now is transition it into what does this chapter do, right? And what we're going to basically be asking is, when does a reaction, or actually any process for that matter, happen spontaneously? And we use 2 things to do that, and we summarize it as what's called free energy. So we use the enthalpy of reaction. So that's like the delta H. So you can think of delta H as different levels. And if you have a ball on a hill like this, right, and you're asking yourself, will the ball roll down the hill? Well, provided there isn't any activation energy, like at some point, yeah, the ball will roll down the hill, it'll end up at this level. and this would be the delta H. This is high potential energy. This is low potential energy. And chemical energy is a form of potential energy. It's stored energy, right? So when we look at this difference, what we say is, well, delta H is negative. That means the products are lower in energy than the reactants. And at some point, given enough time, that ball will probably roll down that hill and end up at the low potential energy side. And this really is how enthalpy works in a chemical reaction. Ignoring the activation energy, right, does the ball roll down the hill? And the answer is eventually, yeah, it would roll down the hill. These kinds of reactions are often spontaneous. So if that's true, right, if exothermic reactions are spontaneous, then are all endothermic reactions non-spontaneous? I mean, can you ever get a ball to roll up a hill by itself? And on the physical sense, like when you're looking at a ball, I'm not going to make the hill as big, but it could be, just because I'm running out of space already because I know what else I'm going to write. And you're wondering whether or not it could roll up this little tiny hill. Well, let's say you do see it roll up the hill. That would be spontaneous, right? Now, in chemical reactions, we can fiddle around with concentrations, right? So when we have a reaction at equilibrium and we manipulate the reactants and products, we can make a reaction spontaneous in the forward direction, or we could make it go in the reverse direction as well. Okay, now the reverse direction is something we refer to as not spontaneous but non-spontaneous. So depending on how we write the reaction, right, reactions are always either spontaneous in one direction or the other direction. So the way we've written the reaction tells us if it's going in the forward direction from reactants to products like this, that's a spontaneous reaction. But that same reaction, if I wrote it backwards, right, would be non-spontaneous, that it's going in the opposite direction to become spontaneous. So back to my little ball on the hill, right? Let's say there's a strong wind, then there's a possibility, right, that the ball could roll up the hill, and endothermic reactions can be spontaneous. Now, how does that happen? Well, if you think about, first of all, the observation that you can buy a cold pack, right, a chemical cold pack, and you can snap it and it gets cold. So that actually tells us that spontaneous reactions are sometimes endothermic. And the key to this, and sort of the unseen force up to this point, is something called entropy. And entropy is the other half of the equation. And entropy really, the term that often gets associated with entropy is the idea of disorder. I never liked the term disorder for this kind of, sorry, I just realized mental disorders over here. Yeah, we use the word disorder a lot, right? So it's a state of confusion. Well, that doesn't apply, right? As a verb, it's a disrupt the systematic functioning or neat arrangement. And often what they say is entropy is a measure of disorder. Okay, so a measure of disorder is not disorder. The term that I like is availability of states, okay? And really it has to do with choice. If you have, let's say you had two levels of energy and they're the same, right? And you're standing here, and you have to go left or right. Which way are you most likely to go? And the answer is, well, you're going to go equal probability of going to the left or to the right. So this would be the reactant side. or the product side. You'll either be in the reactant side or the product side. Again, if everything's the same and the energy is equal, and you're looking at it like this now, you have pathways. You can go either, I just realized reactance looks like right too, but if you can either go left or right, okay, but what happens if it's like this? You're in the middle, and you could go left or right or right or right or left, like that. And you're just looking around yourself and deciding which way you're going to go, right? There are more states available over here. So let's say all of them are of equal desirability for you. Okay, you have an equal probability of going down any of those, then your chance of going to the product side is greater than your chance of going to your reactant side. And so we talk about this term availability of states in entropy. The more states that are available, the more likely that you are to go into one of those states. So this effect, right, can be actually big enough that if a reaction is endothermic, but there are more states available in the product, right, then it'll go in the forward direction. You're like, well, what kind of things are those, right? Take, for example, evaporation, right? Evaporation, if there's liquid and no gas phase, well, the gas state has a lot more availability of states because the freedom of the molecule is greater. And so liquid will naturally evaporate until it comes to sort of a vapor pressure where it's at equilibrium, okay? So, but evaporation is an endothermic process, so it's absorbing energy. It's definitely not giving off energy, because when you have water on you, for example, and it evaporates, it cools, right? So you know it's an endothermic process. But the fact that the availability of states of the liquid being as water as H2O versus as water as a gas, the availability of states in the product state is so much higher than the reactant state, then evaporation will take place spontaneously under those conditions. Okay, so these are the two things that we're looking at. And it turns out the free energy is a measure of kind of both. Okay, you combine the enthalpy and the entropy, and we create a term called the free energy. And I'll show you this on the next slide. But I just want to go over a couple of things before we move off this slide. When is something spontaneous? Well, we've already sort of decided. I'm going to make a little grid here. All right. We're going to have delta H up here, and we're going to have delta S here, and we're going to break it into a grid like this. Now, delta H can be negative or it can be positive, and delta S could be negative. Oops, I guess I probably shouldn't do it that way. Negative, or it could be positive, like that, right? Now, if delta S is positive, that's something that favors a reaction being spontaneous. So this is favoring spontaneous. There's an unfortunate line there like that. Okay. On the other hand, we said if delta H is negative, that favors spontaneous. And you notice the intersection of delta H being negative, that's here, right? And delta S being positive, that's here. It turns out these reactions are always spontaneous the way they're written. Because none of the factors in delta S or delta H, right, favor something not being spontaneous. Oh, by the way, I think I forgot to say this. Entropy is usually listed as S, and the change in entropy is delta S, right? Now, let's say you have a situation where delta H is positive, right? That doesn't favor spontaneous reaction, but delta S in being negative, right, going to less disorder or more order is also not spontaneous. So it turns out this grid here, right, this is doesn't favor, or we'd say non-spontaneous for delta S, and this is non-spontaneous for delta H. That intersection is right here. So what does that mean? It turns out that means these are never spontaneous. That means the reaction is both endothermic and creates more order, and those are things that can't happen and be spontaneous. So this is kind of like a lot of like stuff in your head, right? Because it's difficult to think about processes in terms of entropy and enthalpy and like have them be separate. But if you can separate them out, it gives you a good guideline about when things are spontaneous and when things are not spontaneous. Now, it turns out there's two other grids here, two other parts of the grid here. This is the situation down here where entropy favors it being spontaneous, but enthalpy says it's not. And over here, this part of the grid says, well, entropy says it's non-spontaneous, but enthalpy says, delta H says that it can be. So how do you know in these two portions of the grid whether or not something's going to be spontaneous? And the answer turns out to be temperature. And temperature sort of is the key to understanding this relationship between when something will be spontaneous and when something won't be spontaneous. So, having said that, okay, you can break it down, the equations, as there's enthalpy, that's heat energy, right? Products minus reactants, we already did one of those. That'll tell us delta H. Well, that table that we looked at also has S values in it, and we'll talk about why these are S and not delta S later. But entropy can be calculated for any reaction the same way enthalpy can, and so delta S is, again, products minus reactants. Again, you have to take into account the number of moles. I don't do, that just makes it too messy, but the concept is that entropy, total entropy of the products minus the total entropy of the reactants tells us whether or not it's going to favor or not favor. Okay, so exothermic favors, endothermic doesn't, increasing entropy favors, decreasing entropy doesn't favor. Now, the way free energy boils this down is it creates one equation that relates delta H and delta S to spontaneity of whether or not a reaction will take place. And if you'll look at the table, there's also columns for the free energies of formation. And if you have that, it's just products minus reactants. So what's the key here, right? When is something spontaneous? When is something not spontaneous or non-spontaneous? It means spontaneous in the reverse direction. And it turns out if delta G is negative, the reaction will be spontaneous. So again, if this is negative, that favors a spontaneous reaction. If delta S is positive, that would become even more negative. So this is a situation that we're talking about back here. Delta H negative, right? Delta S positive, these are always spontaneous. Now, for those situations where delta H or delta S disagree with the spontaneity of the reaction, they don't agree with each other, right? Then that's when temperature becomes important. And that's what you'll be using in the grid at these points here and here. So one of the things about my slides that you guys aren't seeing because you're not seeing this in class is there's actually sounds that play. So I'm going to have play in this particular slide is the sound that is associated with this slide. So I wanted to give you sort of a graphical representation of what this looks like.
The information you hold could alter man's destiny. I will do anything to possess it.
Okay, so one of the things we said in this equation is, for this equation, if delta S is positive and delta S is negative, the reaction is never spontaneous. Now, if you think about what that means, delta H would be positive, delta S is negative, so you alter the sign here. But as temperature changes, right, if you go from lower temperature to increasing temperature, then it's always the case that delta G, right, will be positive or non-spontaneous. The only way you can make it be spontaneous if somehow you could take this thing all the way back to negative temperatures, Kelvin. Now, on the other hand, the other side is also true. That is, if delta H is negative and delta S is positive, then what happens is as temperature increases, delta G becomes increasingly more negative. And as a result, those reactions are always spontaneous. The times where temperature changes the spontaneity are when, for example, delta H is positive, right? But delta S is also positive. And in those instances, this value of delta S as temperature increases will cause a decrease in the free energy until eventually crosses zero. That's supposed to be zero here. And when it crosses zero, it goes from being non-spontaneous, we say, to spontaneous. And it can also be that if delta H is negative, but delta S is negative as well, they have the same sign, I don't know if you realize that, then what's going on is the temperature, as the temperature increases, the free energy, delta G, increases. Now, here's the interesting thing, right? At this point here, either if it's the slot going downward or the upward, doesn't really matter. This is the point where delta G is equal to 0. And you can actually solve this equation to decide at what temperature the reaction changes from being spontaneous to non-spontaneous or non-spontaneous to spontaneous. Or just to say it simply, the spontaneity of the reaction changes. Okay, one more thing before we leave this slide. One of the things I wanted to talk about is the idea of reactant favored and product favored in terms of the free energy. So when we say a reaction is spontaneous, we're saying it's going to form products, a lot of products from the reactants. And so in essence, this is what we mean by a product favored reaction. On the other hand, if delta S or delta G is positive, right, that means it's reactant favored because not a lot of non-spontaneous doesn't mean that no product can form. It's just not very much product will form until it comes to equilibrium. So it turns out the free energy is directly related to the equilibrium constant of the reaction. So think about this, the phrases I put here. I have a reaction of A plus B goes to C and D, right? If we only have A and B, right, think about all the ice tables we've done where we just have reactants. Then the reaction goes to the right. You have minus X, and then plus X, right, underneath these terms here. What that means is the reaction is spontaneous. On the other hand, for the same reaction, right, if I put C and D in the mixture and no A and B, then the reaction goes to the left. So this top one goes to the right, bottom one goes to the left. That's what we mean by non-spontaneous. It's spontaneous in the reverse direction. And for the same reaction, right, we can make it either spontaneous or non-spontaneous by fiddling around with the concentrations of reactants and products. And it turns out the free energy of a reaction, okay, is related to the reaction quotient, the products over reactants reactant quotient that we did from equilibrium constants. So the equation looks like this: is the free energy of a reaction at any given set of concentrations, so that's where Q comes in, is equal to the standard free energy of the reaction plus RT ln Q. Now, we'll talk more about the standard free energy of the reaction. But what happens if delta G is 0? That means the reaction is not spontaneous, that is not going to go forward, and it's not going to go back. And what do we call that, right? We call that equilibrium. So at equilibrium, delta G is 0, and we can rearrange this equation to be delta G 0 of the reaction is equal to minus RT ln instead of Q. Now we can put K in because the system's at equilibrium. So that covers sort of all the chapter in a nutshell. And my advice would be watch it at the beginning here like you are now. And then after you go through the next two segments, just come back and watch the second half of this video to sort of review all the material that we've covered. Now, I just want to point out, I do have other old slides back here, like this one and this one, and a couple of others. Ooh, what happened to that slide? Interesting. And in these slides, in the notes to them, I actually have the problem worked out. So if I upload the PowerPoints for these, you can actually use these as sort of like a study tool. Anyways, after this now, we'll sort of start with officially what the chapter is and the second set of slides. So this is the first set. Now you'll go to the second set, and there's actually 3 sets of slides for this chapter.